Let me open our sessions and let me give the invite first speaker, Tomohiro Inagaki, Hiroshima University from Japan. We're all listening to you. Can you begin your talk? Do you hear me?
Thank you.
Professor Tomohiro, could you begin?
Yeah?
Yes, we listen to you.
Okay, thank you for the opportunity to make this presentation today. I talk about the inflationary expanding universe by complete scalar field. So the main part of this talk is based on the work collaboration with Sergei Olinton and Hiroki Sakamoto. And this is the outline of my talk. And I want to talk about, consider the gauge non-Yonarashino model to describe the complex scalar field. The main point of my talk is how to apply the model to the inflation era of our universe. Then I show some numerical results for the cosmic microwave background fluctuations. Okay. For introducing my model, I will review inflation universe very briefly. The idea of inflation has been introduced to solve some cosmological problems. Why our universe is so flat, why the universe is homogeneous and isotropic, and no lyric abundance of any exotic particle is observed, and so on. So, the inflation is introduced to solve these kinds of problems. One of the evidence of the inflationary expansion has been observed in the cosmic microwave background, CMB. Inflationary expansion can be induced by the potential energy of so-called inflaton field. It immediately cools down the universe. After the end of inflation, the potential energy is released. So the universe is reheated again. Then the universe, after that, the universe cools down, and the proton catch the electron and combine the neutral hydrogen atom. After that, the photon propagates freely. We observe the photon as a cosmic microwave background. And it is considered that the fluctuation of the cosmic microwave background is originally generated by the quantum fluctuation of the inflaton field. So there is a possibility to test the model of inflaton from the thermal fluctuation of cosmic microwave background. In a slow-roll approximation, it can be described, thermal fluctuation can be described by the inflaton potential and its derivatives. So now we come to the main point of this talk. I introduce the gauge NZ non-Yonarashino model and regard the obtained effective potential as the inflaton potential here. So we consider the gauge theory with NS fermion flavors and assume that one of the gauge structure, I write it G here, is strong enough to describe it by four-fermion interaction. So we start from this Lagrangian. It is called the gauge NZ model, and I consider it scale-up model of QCD-like theory, and we normalize the four-fermion coupling in this way for convenience. According to the auxiliary field method, the model can be rewritten by this Lagrangian. The auxiliary field sigma and pi indicates the composite scalar and pseudoscalar field. I note that the original Lagrangian Gauge-NZ model can be reproduced by substituting these classical equation motions here. Please compare this Lagrangian with the Lagrangian for the gauge Higgs equal Lagrangian. Then we found these Lagrangians coincide if we drop the kinetic term and curvature interaction and positive coupling, and also normalize the Yukawa coupling Y and mass scale M square. So this Lagrangian coincides with the Lagrangian obtained from the Gauge-NZ model. It can be achieved by the Wilsonian renormalization group. To show the equivalence, it is more convenient to transform the field in the gauge Higgs or Lagrangian in this way. Then we get this form of Lagrangian, and we solve the renormalization group equation. Then it has been found the solution of renormalization group equation to satisfy these conditions. Under these conditions, you can see this term disappears. So it means that the gauge Higgs-Yukawa model coincides with the Gauge-NZ model at the completeness scale lambda introduced here. This is the schematic image of my assumption. The Gauge-NZ model can be described by gauge Higgs-Yukawa model with completeness conditions. I assume that the model dominates the energy density of our universe at the inflationary expansion era and adapts the chaotic inflation scenario of this model. Okay? I also impose the following assumptions. We neglect the learning of the SN gauge coupling, and we consider the completeness scale is large enough and take the lambda infinity limit. We keep time up to linear in term in R and drop higher order term in R. We also assume that only the field sigma contributes the inflationary expansion here. Then we get the renormalization group improved effective potential. Parameters of the model are the constant gauge coupling alpha, for fermion coupling G4, and the number of fermion flavor NF. NC is the color of SU NC, and the renormalization scale mu here. We have 5 parameters in this model. I use this potential to calculate the CMB fluctuation numerically. We employ the slow roll scenario. I have no time today, so I can only show some keywords. Please see our paper for details. The CMB fluctuation can be evaluated in the following way. First, we define the metric tensor of the frame in so-called the Einstein frame. Then the exit end of the information is found by evaluating the so-called slow roll parameter. Epsilon and eta is order unity. The value of the field sigma, initial value of the field sigma is fixed to generate a suitable E-folding number. It is necessary to solve the horizon problem. Then we calculate the density fluctuation, spectral index of fluctuation, the ratio between the tensor and scalar type fluctuations, and the running of the spectral index. So, as I said before, the models have 5 parameters. These parameters, we evaluated the CMV fluctuations as these parameters vary. I note that the mass scale is normalized by the Planck scale. First, I show the typical behavior of the effective potential. If we consider case NF times NC is larger than 24 pi square or NZ limit, the potential has such kind of the behavior. Local maximum observed. In this case, we need to fine-tune the initial value of sigma near the maximum. So, to avoid the fine-tuning problem, we consider only the case NF times NC is smaller than 24 pi square here. In this case, we found the slope of the potential decreasing as the gauge coupling alpha decreasing. It means that the smaller gauge coupling generates a smaller fluctuation, so we can tune the amplitude of the density fluctuation by the gauge coupling alpha. So we numerically evaluate the density amplitude of the density fluctuation delta. It should be order 10 to minus 5th from the observation. So if we take the alpha is order 10 to minus 12th, delta is almost 10 to minus 5th. So we fix the gauge coupling alpha at the order 10 to minus 12th to reproduce the observed amplitude of the density fluctuation. Next, we consider the dependence of four-fermion coupling and energy scale mu. In this table, we show the amplitude of the fluctuation delta and the spectral index NS and tensor to scalar ratio R, and also the learning of the spectral index alpha S. And here I only notice that all the results are consistent with the observed data observation Planck 2015. Here we vary the renormalization scale and the four-fermion coupling. All the value is almost fixed. And today I have no time to show the NC and NF dependence, but these parameters also have no large contribution for in the case NF type NC is smaller than 24 pi square. Now I come to the conclusion. Today I applied the complete scalar model to the inflationary expanding universe, which shows the numerical results for the CMV fluctuations under the slow roll and the other approximations. Then we found that the gauge coupling alpha should be the order 10 to minus 12 to generate a suitable density fluctuation. We obtain a consistent spectral index tensor to scale ratio learning of the spectral index with the Planck 2015 data. The validity of some approximation considered here is not so clear, so we should consider the lower complexity scale. In this case, we observe larger parameter dependence. We show some result in the abstract. And the scale-up model of the QC-like theory, there are many meson and barium-like composite fields. So it may be interesting to consider the multi-field model of information in this model, and we should introduce some standard model field and discuss the reheating and preheating error. And it is also interesting to extend the model with some dark matter candidates. Thank you.
Thank you very much, Professor Takamura, for your very interesting talk. And I want to ask, have any questions for Professor Takamura? Yes.
I have a question. Dr. Takamura, when you said about density, what order of density you consider it? Which density you consider it? For example, it could be density for quartillion plasma.
You mean the density of the inflaton field here?
What? I'm asking about scale of density. What density you consider it?
It's much larger than the quark-gluon plasma. The typical scale of inflation is 10 to around the Planck scale.
Thank you.
Yeah, so much larger than the quark-gluon plasma we consider here. So I say it's the scale-up model of QCD light theory.
Thank you. So I have one question too. In the slide 7 or 8, you talk about the low energy and high energy. What do you mean when you talk about low energy in the figure? What do you mean?
Okay.
Yes. Next slide. What? Low energy and high energy. What do you mean? Yes.
High energy means the beginning of the universe. I mean, low energy is it's near the beginning of the universe. Then inflationary expansion occur around here. Then reheating and decombination occurs, and now we are much low energy scale, between the low energy scale.
But in scale, it's how many is energy? What is in scale? In figure, how many energy? In GeV, in scale, yes. In scale of energy, yes.
Yes, high energy means almost the Planck scale.
Okay.
Planck scale. And because of the inflation, low energy, it is also the high energy compared with the usual QCD scale. And usually we consider the reheating energy temperature is almost 10 to 11 GeV. So low energy is also very high.
Yes, thank you very much. You have any questions? Okay, next.
I have one question. So, is it possible? So I would ask. So, is it? Okay. So about cosmological constant. Cosmological constant is same as in usual inflation theory, or it depends on the density or some other parameters.
About the cosmological constant.
Yeah.
Does it expansion by the potential energy of the complete scalar field? So I don't introduce the cosmological constant here. Any cosmological constant.
Okay.
So the cosmological constant energy induce inflation expansion.
Okay. Okay. Thank you.
Thank you very much for your answer, and we're proud that you take part in our conference. Thank you.